Okay, so we're going to do lesson 4, increasing, decreasing, and concavity. F is increasing if this just means that a y value at x1 is less than the y value at x2 as long as you're going from right to left. This is what this means. So increasing, most of you just know that f increasing means that you have a function that is trending in the upwards direction as you read from right to left. If f is increasing, then the derivative is going to be greater than 0. So that means that the derivative is positive. If f is decreasing, then the y value is going to be bigger on the left side, and it's going to get smaller as you read from right to left. So this is going to be going down. Most of you know that as kind of like decreasing slope, or decreasing is like negative slope. So that means that the derivative is going to be less than 0. That means that the derivative is negative. If f is constant, if the y values are equal when you have two different x values, that means that your first derivative is going to equal 0. This is 0 slope. So that means that your slope just looks like a straight line. Okay? Don't worry about this right now. We'll talk about this later. If you want to read through it, you can. We're going to do example 1. So it says, determine analytically where f of x equals x over 1 plus x squared is increasing or decreasing. Well, in order to find that out, I need to find out when the first derivative is positive and when the first derivative is negative. First thing I'm going to do is I'm going to take the derivative of this function. So f prime of x equals quotient rule 1 plus x squared times 1 minus x times 2x all over 1 plus x squared squared. Okay, that simplifies to, let's see, 1 plus x squared minus 2x squared all over 1 plus x squared squared. That's negative x squared plus 1 over 1 plus x squared squared. And let's factor out the negative. And then the top factors into negative x plus 1, x minus 1, all over 1 plus x squared squared, right? So if that's the case, then the first thing I'm going to do is I'm going to find out where my first derivative ends up being 0 or undefined if I have an asymptote, because those are the two places that it'll change from increasing to decreasing, when the first derivative equals 0 or when the first derivative is undefined. So if I set the numerator equal to 0, then I'm going to get x equals plus or minus 1. And if I set the denominator equal to 0, then I'm going to get no solution. So the only two possible places that it'll change direction is at positive or negative 1. Now what we want to do is we want to do a number line, because that's always the easiest way to tell. Always label your number line. So I'm going to label it f prime of x, because that's where we're getting all of these numbers from. And then we're going to put a negative 1 on this side and a positive 1 on this side. And then what we want to do is we want to test values. So I'm going to test values on each one of these intervals in any one of these derivative equations to see whether or not I get a positive or a negative number. So if I'm going to do some test values, I'm going to do it right here. These are just going to be my test values. I'm going to do -2. Okay, so if I plug in -2 for x, then let's just say this equation. Any one of the derivative equations are going to work, but I'm going to plug it into this one. So -2 squared plus 1 over 1 plus -2 squared. This is going to be, up here is going to be a negative number. And then on the bottom, it's going to be a positive number. Right? So that means that a negative divided by a positive is a negative. This is going to be negative right here. Then in between 1 and -1, I'm going to choose an x value of 0. And so if I plug 0 into any one of the first derivative equations, I'm going to get a -0 squared plus 1 over 1 plus 0 squared. That's going to be a positive value over a positive value. That's positive, so it's going to be positive here. And then if I plug in, let's say 2 for x, then -2 squared plus 1 over 1 plus 2 squared. That's going to be a negative over a positive, which is a negative, so this is going to be negative. Alright, so what that means is that I'm going to have on this side, I'm going to have negative. That means I'm going to have decreasing slope. So right down here, this is going to be going down. In between 1 and -1 and 1, I'm going to have increasing slope, so we're going to be moving up. And in between 1 and infinity, we're going to be going down. So this is what our graph is going to look like. It's going to be decreasing, increasing, and then decreasing. And anytime it says determine analytically or explain your reasoning, I want you to do an explanation. You say decreasing on the interval -infinity to -1 and 1 to infinity because f prime of x is negative. And then you say that the function is increasing on the interval -1 to 1 because f prime of x is positive. Okay. So you always have to explain your reasoning. This number line chart is not enough to explain your reasoning. You do have to include it to show your work, but this is the explanation that I really want. Okay? So that's increasing, decreasing, and constant. Let's now talk about concavity. So for concavity, if the first derivative is increasing, then the second derivative, so that means that the second derivative is greater than 0. The second derivative is positive. The graph is concave up. Concave up means that any part of the graph looks like this. It doesn't have to be the full graph, but most of it looks like it could hold water. It's concave up, like a cup. If f prime is decreasing, or the second derivative is less than 0, the graph is concave down. That means that it looks like a frown. So concave up, like a cup, concave down, like a frown. These are the ways that you're going to explain concavity. You're going to either explain concavity that f prime is increasing or f prime is decreasing, or you can say that the second derivative is positive or that the second derivative is negative. So these 4 ways very important, are the ways that you explain concavity on a graph. A point where concavity changes is called an inflection point. If there is an inflection point, then the second derivative is going to equal 0 or undefined, and then it's going to change from positive to negative or negative to positive. Okay? Just because the second derivative equals 0 does not mean that there's a change in concavity. For example, if you took the second derivative of x to the fourth, the first derivative is 4x cubed. The second derivative is 12x squared. If I plug in 0 for x, I'm going to get, or if I set this equal to 0, then x is going to equal 0, right? But if I did a number line with the second derivative at 0, and I plugged in -1 in here and 1 in here, I'm going to get a positive number and a positive number. So the second derivative stays concave up, then zeroes out, and then goes concave up again. That is not an inflection point. An inflection point has to change concavity. Okay? All right, so let's do example 2. Let's determine the concavity and inflection points of this function right here. Before actually solving this, the first thing I'm going to do is I'm going to make it x to the 2/3 minus x to the 5/3. Because I think that's easier to solve than doing product rule, because I'm going to have to do a lot of manipulation. I'm going to need the first and second derivative, and I don't want to do product rule and have to simplify. So the easier I can make it on myself, the better. All right, so this is f of x. I'm going to find the first derivative, 2/3 x to the -1/3 minus 5/3 x to the 2/3. And then the second derivative, -2/9 x to the -4/3 minus 10/9 x to the -1/3. And if I just make this easier for me to manipulate, -2/9 x to the 4/3 minus 10/9 x to the 1/3. And then to get these two to combine, I'm going to multiply this one by x, and so now I'm going to get the equation -2 minus 10x all over 9x to the 4/3. Okay, so concavity is going to happen when it changes from positive to negative. An inflection point may happen when the second derivative is 0 or is undefined. So let's find out when it's 0. So let's set the numerator equal to 0. Oops, not -2x minus 10, -2 minus 10x. And let's solve that. So 1/5, add the 2, -1/5 equals x. And then let's find out where the second derivative is undefined. Let's set the denominator equal to 0. So x has to equal 0. So we're going to do a number line for the second derivative. All right, so all my values on this number line are going to come from my second derivative. Here's -1/5. Here's 0. And then we plug in values To the left, in between, and to the right of it, I'm going to get a positive, a negative, and then a negative. Okay, so what that means is that in this section of the graph, I am concave up. In this section of the graph, I'm concave down. And in this section of the graph, I'm concave down. There's only one point where I'm going to have a point of inflection, and that's at -1/5. Okay, since I need an actual inflection point, I have to find the y value, and you always find the y value by plugging it back into the original equation. And if it's a free response, remember, you don't have to simplify, so we can just plug it straight in and then just leave it. That's our xy point. Concavity, so it's going to be concave down on the interval -1/5 to 0 and 0 to infinity. We're not going to include 0 because remember it's undefined at 0. And then it's concave up from -infinity to -1/5. Okay? All right. That's increasing, decreasing in concavity. Now let's take a look at relative extrema. So you're going to have a local maximum or relative maximum if it satisfies either the first derivative test or the second derivative test. And you can have a local minimum if it's the smallest value in a certain section. So if I were to draw a graph kind of like this point right here would be my relative max, because it's the maximum relative to the area that it's around. And this one right here is going to be my relative min. It's my lowest point just relative to the area that I'm around, or locally. So it's the smallest point locally. Both of these are called extrema. So sometimes they say find the relative extrema. I think example 1 says find the relative extrema. So if that's the case, then you're looking for both the maximum and the minimum. Now a critical point is going to be any place where the derivative is 0 or undefined. Okay, so if the first derivative equals 0 or undefined, then the original is going to have a horizontal tangent line, or it's going to be not differentiable. What the first derivative test says is that if you have a critical number, meaning that if the first derivative at some number c equals 0 or undefined, then you can apply the first derivative test. And if the first derivative changes from negative to positive, so think if the first derivative is negative, it's decreasing, to positive, that means it's increasing at x equals c, then you're going to hit a relative minimum. Well, that makes sense because you're going down, then your first derivative is either 0 or undefined, and then it's going up, so it's a minimum. If the first derivative changes from positive to negative, that means that it starts with an increasing, and then to negative, then it starts decreasing. So if you're going from increasing to decreasing, then you're going to hit a relative maximum. Sometimes I find that drawing these lines helps you figure out whether it's a minimum or a maximum. Note, the maximum and minimum values are the y values. So if it asks you what is the minimum value of such and such, then you're looking for the y value. If it asks you what's the maximum value of this function, then you want the y value. The x value is where the minimum or maximum happen, and then the y values is what the values actually are. Okay, so let's find the relative extrema for this polynomial right here. So first thing I'm going to do is find my critical values by taking the first derivative. So negative 6x squared plus 6x. Find the critical values. We're going to set it equal to 0. And then so I'm going to factor out a negative 6 and an x. And so we have x minus 1. And so x equals 0 and 1. All right. Now, after we do that, let's do a number line with 0 and 1. Here's my first derivative number line. Make sure you label it. And let's pick numbers. So if I pick negative 1, then this is going to be negative 1 squared is positive. Positive times a negative is a negative. And 6 times negative 1 is a negative. So a negative plus a negative, that's going to be decreasing. In between 0 and 1 is like 1/2. Maybe it's easier in the factored form. So negative 6 times 1/2 is a negative number. 1/2 minus 1 is a negative number. A negative times a negative is a positive. So it's going to be increasing from 0 to 1. And then plug in 2. And negative 6 times 2 is a negative number. And 2 minus 1 is a positive number. So a negative times a positive is a negative. So really our slopes are going decreasing, increasing, decreasing. That means I'm going to have a relative max at 1 comma, because you're going to go increasing to decreasing. And then we need to plug 1 back into the original equation to get the y value. So negative 2 plus 3 is 1. And we're going to have a relative min at 0 comma 0. Okay. It doesn't ask you to explain or justify your answer, so we don't have to write anything extra. But if it did say justify your answer, then you would want to explain this number line chart in full detail. Okay, so that's the first derivative test. You can also use what's called the second derivative test. So this is another way to find maximums and minimums. If the function is a twice differentiable function, if the first derivative equals 0, so that means that either the first derivative, or if the first derivative equals 0, and then the second derivative is less than 0, so that means that the second derivative is negative, then f of c is a relative maximum. What this is saying right here, the second derivative being less than 0, means that it's concave down. If you've got a concave down function, and you know that your first derivative has to be a horizontal tangent line, you know that you're going to have a maximum at that point. If your second derivative is greater than 0, that means that it's concave up, right? So if you have a concave up function, your first derivative equals 0, that means you have a horizontal tangent line. Well, that means that you're going to have a relative minimum, right? So sometimes, in order to evaluate, you can't do this number line chart. You might have to use second derivative test to prove whether or not you have a maximum or minimum at that point. So make sure you memorize second derivative test. And make sure you use these words, second derivative test and first derivative test, on your free response answers, because that's good justification for why you have a maximum or minimum at a certain point. Okay. If the second derivative is equal to 0, the second derivative test is inconclusive, so it could have a relative max, a relative min, or neither. We just don't know. Second derivative test isn't going to tell you anything. So what I want to do now is I want to use the calculator to find out relative extrema for g of x equals 1/2 x minus sine x on the interval 0 to 2 pi. Make sure you are in radian mode, and so the first thing we're going to do is we are going to find, what do I need to do? I need to find where g prime of x equals 0, right? Because I need to prove that my first derivative equals 0 at a certain point. So let's just go to y equals, let me clear all this stuff out. And let's type in 0 for the first one, just like we did that last class where we wanted to find the intersection. And then since I haven't actually taught you how to take the derivative of this, what you can do is you can do, in here you can graph derivatives. If you just type in math, get your derivative function, d dx, and let's type in 1/2 x minus sine x, and then for x equals, just type in x equals x. So then it's going to graph it at every x value. I might as well change my window from 0 to 2 pi, because that's all I want to really look at. So if I graph that, it's going to take a little while because it's calculating every derivative at every pixel. So we have two intersections, one right here and one right here. Let's do second calc intersect. I'm going to find both of them. First curve, second curve, guess. So x equals 1.047 and x equals going over to this side. .236. Okay, now I need to find the second derivative at that point. So let's go back to y equals. In y3, I want the second derivative. So I want the derivative of this derivative. What I'm going to do is I'm going to turn these off because I don't want to graph them anymore. So in y3, I'm going to do math, go to nderiv, and we're going to take the derivative. Now I want, for the second derivative, I want to take the derivative of the first derivative. So I'm going to do d dx of, and I'm going to go grab this. You can do that, I think either alpha f4 gives it to you. So I want to choose y2. Or if you don't know that, there's a vars button. So if you go, that means variables. And then you go over to yvars function, and then you can grab y2. So it might be easier if you just go alpha f4 and then grab y2. Still x equals x when you're graphing. And then we're only going to graph the second derivative. It's going to take a while. Just sit tight. Okay, so I'm going to press trace, and then I'm going to type in 1.047. that gives me a y value of 0.8659. This is going to equal 0.8659. And then at 5.236, I have a y value of negative 0.866. What this means, if we interpret from this data, then that the second derivative is positive here, and the first derivative equals 0. If the second derivative is positive and the first derivative equals 0, then I have a concave up graph with a horizontal tangent. That means that this is going to be a relative min at 1.047. And then this one, the second derivative is negative, and the first derivative equals 0 because that's what I solved for. So we have a concave down graph with a horizontal tangent line. So I'm going to have a relative max at 5.236. I should probably get the y values, so I'm going to go to my home screen and just type in minus sign of so negative 3.342, and then get the same equation with 5.236, 3.484, and those are your two relative min, relative max values. Okay, that's second derivative test. All right. We are going to have you do these. For this question, just cross off this and try to answer the problems. Solve this one if you can, and then sketch the graph. What I want you to do is I'm going to post the answers to this key on Blackboard. After you finish this practice, check your answers on Blackboard and see if you got the same thing, because I've basically taught you everything you need to know. I don't want to make this video any longer than it needs to be. And if you have any questions on this page or any of the homework problems for, what is this, increasing, decreasing in concavity, if you have any questions on that, then I'll answer that next class. Okay, thanks guys.